In this example, we're going to show how we can use analytical models to help validate our unconventional gas um, interpretation. In addition, the models can be used to generate forecasts and look at alternative scenarios, test sensitivities to unknown parameters such as permeability, fracture length, area, adsorbed gas, pressure-dependent permeability, all kinds of more complex properties like that. So we're going to start with a relatively simple case. We have here basically linear flow. Our square root of time plot indicates a straight line with a positive y-intercept indicating that there's some skin associated with this completion. We're going to set the extrapolation on the flowing material balance such that the green line is right at the end of the data, and that should give us our minimum stimulated reservoir volume. Our type curve is shown at the bottom, and then our production forecast shown here in red is very likely our P90 forecast. And that equates to a stimulated area of about 41 acres. Now I'm going to go ahead and enter in some of the well properties, the wellbore length, which is 4175, the number of fracture stages, and now Harmony calculates the matrix permeability for me based on the numbers that I've put in here. And this is a method that we can use to seed the analytical model. So I'm going to go ahead and create an analytical model. And the model of choice here will be a horizontal multifrac composite model. The composite model is nice because we can do two permeabilities, one on the inside the SRV, an effective permeability inside the SRV, and a matrix permeability outside of the SRV. So we're going to start by just modeling the SRV, a very simple model. And to populate the numbers into this model, we simply click on D, put in the reservoir properties, click on D again, and fill in the UGM VP properties. And we now have our model created. And our history match is showing here. At the moment, we don't have a good match of the data, but it's very easy to refine that match. I'm going to set FCD and K1 as optimizing parameters. I'm not going to include XF as an optimizing parameter because that number comes in directly as an input from our UGM. We're going to leave that fixed in place. We're also going to leave K2, which is the matrix permeability, as an anchored parameter as well. But I'm going to allow the model to adjust K1, which is the permeability in between the fractures, and the fracture conductivity until it optimizes a match between the simulated pressures, which are the brown line data down here, and the actual pressures, which are shown here. So we're going to start that process. And if we look in the top right-hand corner, we can see the type curve, which is hopefully going to match, and we're going to see the data matching down here. So we'll let that run for a few seconds, and with any luck, we'll be able to see a decent pressure match developing as we go through. Okay, so we have what looks to be a fairly good pressure match. I'm going to go ahead and stop the auto match procedure from going. There's our pressure history match. We can also show what this looks like as a rate history match by running it as a rate matching model as well. And it's as simple as that. We've now validated our interpretation using this model. If we now want to create a production forecast using this model, we can go into the forecast and test design, create a 30-year forecast. If I want to compare what that forecast looks like against my UGM forecast, I can create a decline curve, a rate versus cum plot, and I will show my multifrac composite model as well as my UGM VP model. And there are both of those models. They end up pointing to roughly the same cumulative gas, total recoverable gas. That is an excellent confirmation that we have done our interpretation correctly.